and industrial sectors. Our second presenter is Devin Pellicone. He is the manager of the product development group at Advanced Cooling Technologies. He has a BS in mechanical engineering from Temple University and an MS in mechanical engineering from Villanova University. He has over 10 years of experience designing and building both passive and active two-phase cooling systems for a wide range of applications. Specifically, Devin has led two-phase cooling programs ranging in power from 100 watts to 100 kilowatts for industries like high-performance computing and power electronics cooling. Devin has 2 patents pending related to two-phase cooling products, and he has authored or co-authored numerous conference and journal papers on this topic. Following the presentation, we'll have a live Q&A with Devin and Brian. You can submit your questions during the session using the chat box on the right-hand side of your screen. We will also provide our attendees with a downloadable copy of the presentation once the session is completed. This will be available in the Resources tab, along with a few other links you can access at any point during the presentation. And keep an eye out for a poll that we'll have later in our session. Well, thank you so much for joining. With that, I'll hand it off to Brian to get us started for the presentation. Welcome, Brian.
Thanks, and appreciate everyone for joining us today. Yeah, I think we have a pretty good session here and would certainly be interested in discussing your thermal challenges in more detail. So please ask questions. And if you don't get the information you're looking for, please reach out to Advanced Cooling Technologies after the session, and we'd be happy to go into more detail on any of the technologies discussed. So today, in terms of agenda, we're going to give a short introduction on who Advanced Cooling Technologies is. This is our first time doing a webinar with EE Time, so hopefully a lot of new audience and faces to ACT. So we'll give kind of a quick introduction on Advanced Cooling Technologies, and then we're going to dive into the details of system level thermal design, challenges within the power electronics spectrum, and then potential thermal management systems and solutions for those challenges. And again, please ask questions as we go along. I think we'll have a good chunk of time at the end to answer any questions. So want to provide the feedback that's best suited for the audience here. So Advanced Cooling Technologies, we're in our 20th year of business. We're a small business out of Lancaster, Pennsylvania, currently slightly over 220 employees. And our focus is thermal management. So we do the entire gambit of thermal management from active to passive cooling solutions. We do everything from research and development through product development and through production. So we're a manufacturer. We're not simply a design or thermal analysis service provider. We do kind of the full spectrum of work. So really, we like to be very incorporated into our customers' needs and understand their system as best possible, so we can provide a custom engineered solution that meets your needs. And as we talk through kind of the industrial power electronics sector, you'll see a lot of the design considerations have to do with not only performance and environment, but also the economics associated with these designs. So we'll go through a lot of that in detail as we explore the technologies, but we do want you to view us as kind of a one-stop for all thermal management. So please bring us complex and challenging problems, and we'll have a solution for you. And kind of building on that in terms of our product portfolio, we'll only touch on a couple today, but again, we do have a lot of various options or tools in the toolbox to bring to our customer base. So we have passive solutions with enhanced conduction or passive two-phase heat transfer to really drive out the delta T's in your system or transport heat from one space to another. And then we're also very well versed in the liquid cooling side with more traditional liquid cooling and chillers to more advanced solutions like pump two-phase technology. And we do have experience in a wide variety of industries. So you'll see some different style of pictures from very ruggedized defense to more commercial or industrial applications. So again, we can kind of handle a lot of the really complex thermal challenges and then have kind of the portfolio of technologies to lean on as we start developing solutions for our customer base. So with that, we'll get into kind of the meat of the presentation. And again, this is focused a lot on power electronic systems. So, and somewhat of a focus on the industrial sector. So in terms of the challenges within power systems or power electronic systems, we actually did a short poll in the industry and came up with these as the critical criteria that designers are looking for. So the first one from a technical side is the heat flux. So there's been a lot of notes or trends in the industry that the heat flux at the component level is increasing, which will impact your junction to case resistance and then your overall thermal budget for your solution, but also the power densities within the system in general. So again, creating a higher heat load to put the onus on the thermal management system. The second area is compact designs. So whereas if you had unlimited space and volume, which we all wish we did, it would be fairly straightforward to design a thermal management solution that can meet your goals. But in most practical applications, we're designing to a constrained volume or a constrained weight factor and need to design the system appropriately. So compact design is certainly a big consideration, and you'll see various examples of unique form factors to consider as we're going through the technologies. The next one here is cost per kilowatt. So this is a term we hear a lot from our customers, and really this is kind of looking at the initial investment cost. So how much does your thermal management system cost, and how much heat can it reject? So with those two factors, it kind of is a cost per kilowatt analysis for the initial investment. And again, the solutions we're looking at are trying to position themselves for these more industrial commercial markets. So inherently, there is a cost benefit. We're not using anything crazy or complex. It follows a lot of the general guidelines or rules of thumb that have been established in the industry. The next area is reliability. So one of the challenges as heat increases in your system is you start going to active systems, and you start introducing mechanical components, failure points, electrical systems. And so there are reliability concerns, but to kind of assess it, we look at the various componentry and try to create the most reliable solution based on the mean time between failure or maintenance routines that need to go along with the solution. So reliability is a key aspect, especially if your system is going into more of a remote location and is not easily accessible. So we understand and work with our customers on those type of situations where reliability might be higher in the trade hierarchy. And the next one is electrical isolation. So as you start dealing with medium or high voltage drives or systems, it becomes a kind of a safety, intrinsic safety matter to make sure that your thermal management system does not introduce any safety risks or shortage risk in your system from an electrical perspective. So a lot of what we'll talk about there is the use of dielectric fluids and refrigerants to combat that challenge. And the final bullet, as a lot of our customers make us very clear on, is the lifetime cost and ownership of thermal management systems. So whereas the cost per kilowatt is typically an initial investment analysis, the lifetime ownership takes into consideration your maintenance cost over time, your replacement cost over time, as well as your energy consumption in these systems. So we'll look at kind of all those different avenues as we go through the presentation and look at different technologies. So this is kind of just a summary of what we just went through, but when we're talking about thermal solutions or thermal systems, really what we're looking for is something that's not going to be eating a lot of energy, because you want your overall system to be cost effective long term, and you don't want to have something that's using a lot of energy to run your thermal management system. In many cases, the thermal management system could be utilizing similar orders of magnitude energy that you're trying to cool down. So it does create somewhat of a compound problem as you start analyzing your thermal management system in conjunction with the overall heat rejection requirements. The next is low maintenance required, again, to drive down that lifetime ownership cost. Low initial investment with the cost per kilowatt. Scalable solution. So this is one that every product pretty much that we'll talk about, especially the dielectric based passive and active two-phase technologies, are going to have a scalable component. So they're very scalable, and we'll show examples of rejecting a couple hundred to a kilowatt worth of heat, all the way up to a couple hundred kilowatts of heat with the same technology, and just scaling the form factor. And then again, we'll look at ROI and levelized cost of energy, the LCOE of these various technologies. And again, just looking for the implementation and usage to match kind of the economics with the system. So here's a kind of a snapshot of more of a grid tie application, but kind of as we go through the technologies, we want to kind of throw the onus that there is a lot of technologies, a lot of thermal solutions being offered and serviced in a lot of these systems, and sometimes they communicate and work very well together, and other times they're piecemeal together. So as we look at things and talk about different technologies, it's also good to have a very complete site-based or system-based approach, because a lot of times you can combine technologies and really drive down those areas we're talking about to provide long-term value to your customers and our customers. So with that, kind of just summarizing what I went through, but what we have seen, and hopefully what we'll portray in this presentation, and what we want you to think about as you're considering some of the options we're talking about, is again taking more of a system level look at the thermal challenge. So many times, if you're putting together various thermal technologies, or if you're looking at one area and then moving to another and having isolated thermal systems, you're actually adding a lot of cost and complexity to your design that could be reduced by taking more of a holistic approach. So at ACT, we like to take that kind of ask a lot of questions to our customers, really try to understand the system parameters, so we can come up with a thermal management system that creates that long-term benefit for our customers. And with that, we'll jump into kind of the technologies and solutions that we talked about. Here's kind of just an overview of the presentation and how we'll progress. So in most cases, we'll be focusing on direct cooling, where the thermal management system couples with the heat sources directly, and then transfers and rejects heat to either downstream or within the thermal management system. But we'll also look at enclosure coolers initially. So these are more low to mid power cabinet coolers, and their big value add is it's circulating air while maintaining a seal. So it keeps everything kind of clean in your cabinet, but does provide air circulation to take heat from the components and reject it to the other side of the cabinet. So starting there, this is more of a kind of product offering slide as opposed to overview of this technology, but we'll go into some applications in the next slide to talk about where and when you might want to use these and the background technology that goes into them. But in general, we have two product offerings for enclosure cooling. And again, these are solutions that couple onto your cabinet that you can kind of see there on the left side. And it does provide a NEMA or IP rated seal, and it exchanges heat between the inside and outside of the cabinet. So there's two kind of categories of cooling. One is above ambient cooling, where you don't need to cool your cabinet below the ambient air temperature. So there you can simply exchange heat through above ambient coolers. So the one you're seeing to the left is called our heat sink cooler, which just relies on circulating air inside the cabinet to collect the heat, conducting through a baffle plate in the middle, and then another fan on the outside to reject the heat to ambient air. So a fairly straightforward technology, and more of an economical solution for customers. But again, in these cabinets, it's usually not a ton of heat. So solutions like this can reject the heat load and be kind of a drop-in replacement for what's going on in your system. The second one in the above ambient is our heat pipe cooler. So this one is a top mounted solution, and it actually uses heat pipes within the core of the heat exchanger to effectively transfer that heat. So again, it's circulating air inside the cabinet to collect the heat, but the heat pipes are doing the work to transfer heat to the outside air. And by having that improved heat pipe conduction area, it allows you to have a much more compact design. So if you can mount on top of your system, you can get away with a good amount of heat rejection in a compact form factor with heat pipe coolers. And then the sub-ambient cooling options, there's again 2 options within that spectrum. So if you do need to keep your cabinet lower temperature than your air, the 2 options outlined here are the ones on the left is the thermoelectric cooler, and those use Peltiers or thermoelectrics to provide that solid state cooling. And on the right is your more traditional air conditioners using vapor compression to provide the sub-ambient cooling. And again, these options are all designed to maintain a seal. So the goal of this product line is really to create a clean, cool environment within the cabinet. So if you're in a harsh environment, outdoor, or a very dusty indoor manufacturing environment, it's a really good solution to fairly straightforward, keep your electronics cool by circulating air and taking the heat outside. And just to go to a couple application details on this technology, again, you can see for customers, it's a fairly straightforward implementation. We do provide all the details of these coolers on our website as far as how much heat they can reject at a given delta T. And we also provide the cutouts and drawing patterns so that they can easily install them into your cabinet. So on the left photo here, this is an outdoor drives cabinet, and this was our HSC 68. So it has 3 different heatsink fan combinations on it. And then what you're seeing kind of overlaying on top of the fans is a rain guard for outdoor use application. So again, the customer came to us, specified their heat load in the cabinet and their environmental conditions, and we're able to quickly direct them to a product that would work based on those areas. The second one here in the middle, this is our heat pipe cooler. So on the bottom of the picture, you can see kind of a cross section of the heat pipe cooler, the HPC, and in the copper color, you can see the heat pipes kind of shown there. So the heat pipes are simply straight heat pipes using methanol as the working fluid, and they're going to transfer heat from the hot air inside the cabinet to the cooler air outdoors. And heat pipes, as we'll get to in a couple of slides, is an extremely efficient mechanism for transferring heat. So able to transfer heat at a very low delta T, and again, driving down that footprint of cutout needed on the cabinet. And the example you're seeing there, that's hard to tell exactly where it's going into, but it's a machining factory. So that's going on top of a electronics enclosure that's driving the machinery. And then the final one to the right, this is our vapor compression cooler. So again, more or less an air conditioner, but designed to be fairly narrow so that you can mount it like you see here on a door mount in an electronics cabinet. That a lot of time is preferred because it's usually space that's available and not mounted with electronics and other insulation and everything. So we do have a lot of door mount applications, and you can see there, again, a fairly straightforward cutout and not a lot of intrusion into the cabinet. And our vapor compression coolers run from about 1 kilowatt to 5 kilowatts of heat rejection at a 0 degree temperature gradient. So fairly good capacity for their volume, and again, very easy installation. And I guess just one more thing to mention about our enclosure coolers. They are off-the-shelf products, so you can order them online. And there's also a calculator on our website, and that actually allows you to put in all your various inputs of your environment. So Whereas a lot of times if you're operating indoors, it's a fairly straightforward calculation on the amount of heat you're generating and your indoor air temperature. If you're in an outdoor environment, you have to take things into consideration like solar loading and things like that. So we do have a calculator that provides all those details and will output a product that'll work for you. So yeah, please feel free to play around on our calculator and see if there's a solution that matches. And if not, we could look at some of the technologies we'll get into in the next couple slides. So we talked about enclosure coolers as kind of your air mixing solution. Now we're going to talk about some of the methods for direct cooling. So again, direct is more or less when we're contacting with the electronics directly and then moving that heat away to some type of ultimate heat sink. So the first technology we're going to look at is heat pipe technology. This has been utilized for many years, and I'm guessing a number of the audience is familiar with this technology, but it's an extremely effective heat transfer mechanism. So how it works is you have an evaporator, which shown in this picture is one end of the pipe, but it doesn't need to be an end of the pipe. It could be anywhere that you're introducing heat along the length. But at the evaporator, that's where you'll couple it with your heat source. It'll take in that heat, vaporize the working fluid, and that heat source will create a pressure and temperature gradient within the pipe that'll push the fluid vapor to wherever it's colder in your system. In this example, on the opposite end, which would typically be coupled to a heat sink. And at the heat sink or the condenser end, it would give up its latent heat, condense back into a liquid. It would be trapped within the wick structure. So on the inner diameter of the pipe, there's a porous wick structure that absorbs the liquid and then passively transfers or pumps that liquid back to the hotter region. So again, it's a fully closed loop system that simply operates with the pressure and the temperature gradient. So it provides extremely good heat transfer because of the latent heat of vaporization, but no moving parts, no mechanical actuation. So it is a very reliable and long-lasting solution. And from a thermal standpoint, it operates with about a 2 to 5 degree temperature difference across the length. So as you're considering this compared to like a metal conduction, you can see how you can kind of very easily short circuit the conduction delta T by implementing a heat pipe. And now we'll kind of look at that exact example that I just mentioned. So in many cases in the power electronics world, the goal is to eliminate hotspots. So one of the areas that we've explored a lot is embedding heat pipes into metallic plates, and in most cases aluminum, because it's fairly cost effective and already has some good thermal properties. So by embedding heat pipes into aluminum plates, you can increase the thermal conductivity of those plates by a couple of factors. So aluminum is typically somewhere between 150 and 200 watts per meter K. By implementing heat pipes, you can easily achieve 600 watts per meter K. And in certain cases, if you have long distance heat transfer, you could achieve over 1,000 watts per meter K. So an example of that, as you see on the bottom left figure, these are kind of a single metallic IGBT cooler. So a single IGBT was mounted to those systems. In this thermal model, we used the inputs on both the left and right. The right one was the pure aluminum, and the left one was after it was integrated with heat pipes. And you can see kind of the hotspot elimination there. So the heat pipes with that 2 to 5 degree temperature gradient along the length of the pipe will spread that heat to the extremes of the heat sink. So not only are you eliminating the hotspot and reducing your case temperature of your electronics, but you're getting better fin efficiency from the outer fins in that scenario. So yeah, that's one example that you can see there from a thermal analysis standpoint. And then on the right side, two examples of fielded hardware for this exact scenario. So these were both IGBT cooling applications. The top one was a naval power electronics cabinet, and that one had multiple IGBTs mounted to the backside of what you're seeing here. And it's a little hard to tell, but the fins that you see there are very tight pitched. So this one actually had a high airflow going through those fins, so we're allowed to get a lot of surface area and space those fins out very, very tightly across that. So a very compact design, but again, isothermalizing that entire base and getting the best use of all those fins in there. And then the bottom one, same example, same story, but in this case, it was a natural convection heatsink. So you can see a much more spaced out fin set. And in this application, they also had a fairly uneven distribution of the heat source. So on one fin stack was actually coupled with about 80% of the heat load. So one fin stack was doing a lot of work and had a large delta T, whereas the other fin stack was not doing as much work and was keeping items cooler. So overall, the system had enough fin area, but was still getting hot spots. So what we did is just embed heat pipes underneath those fins and basically exchange the heat. So again, smoothing out that that heat load that each of the fin stacks had to deal with and reducing temperature of the overall conduction gradients and the case temperature. So that's kind of the heat pipe side of things. Another passive two-phase solution, kind of a variant off heat pipe technology, is thermosyphons and then loop thermosyphons. So thermosyphon is the name for a gravity-assisted heat pipe. So in those cases, you do not need a wick structure to return the fluid. You're relying on gravity to return the fluid. And in those cases, it could be very similar. A thermosyphon can be very similar to a heat pipe, just unwicked, and knowing that you need to couple your heat sink above your heat source. So if you have that scenario, you can use thermosyphon technology and get the benefit of the gravity assist. What ACT developed and is implementing in the field is loop thermosyphon technology, which takes it to kind of a higher or more advanced level and enhances your heat transport capabilities even further. So same design principles or considerations here. You're evaporating at your heat source and you're condensing at your heat sink. But because you're running in a full loop and it's designed strategically that when you're condensing, you're continuing the path of the loop, you never have the forces interacting. So your vapor is flowing one direction, your liquid's flowing continuously along the loop. In a heat pipe or a typical thermosyphon, those forces would interact. So your vapor would be flowing down the center and your liquid would be returning around the outside, but that creates some inertial forces within it, which limits your overall capacity. So in the case of a loop thermosyphon, you can move more heat in a similar form factor. Again, other benefits is you can have very long distance heat transport as long, again, as your condenser is above your heat source. It's also a fairly scalable design, and you can have multiple components. And you'll go into some examples where you'll see multiple components mounted to a single evaporator, and the ability to scale this technology from a couple watts to a couple hundred kilowatts. So a very scalable technology that we've demonstrated. And then looking at some examples here, the top one there is a medium voltage drive cabinet. So this had kind of the example I was alluding to, multiple high powered sources on that single evaporator plate. So the metallic kind of silver aluminum plate that you see there coming vertically had 6 heat sources mounted to it. So 3 on one side, 3 on the opposite side. It used refrigerant as the working fluid, and again, transferred that heat in kind of the schematic you saw on the previous slide to an air-cooled condenser. And this one had a fan coupled with it and utilized that heat sink that you can see there with some horizontal airflow. This very similar design can be very flexible, so we can do it with a vertical airflow. We can also do it with a remote condenser with some flexible tubing. So again, a very flexible design as long as you have the condenser above your heat sources. So that exact example, you can see kind of some of the figures there, but had an extremely low thermal resistance, so very low temperature gradient across those areas. And we were able to operate that system between -55 and +50 degrees C and transfer and reject over 11 kilowatts of heat. So a very capable solution in a fairly small form factor. That entire solution fit within kind of a medium voltage drive cabinet with only the condenser exposed to the air environment. And then the bottom solution here, similar type application. This was a 5 to 10 kilowatt cooling capacity. But what we're showing here specifically is the orange hosing that you see. And this was somewhat of what I was alluding to in the last example as well. But you have the ability to have a remote condenser and flexible lines between the evaporator and condenser. So this allows for designers of these cabinets to integrate thermal solutions late when it's already fairly populated and packaged. Also allows you to run fairly long flex lines. So if you didn't want rigid tubing in your system, to allow for you to integrate, manipulate, maintain, clean the cabinet, you have that ability and that flexibility there. So again, fairly scalable design and a lot of different form factors we can work with here. Devin, anything you want to add?
I'll just add on that bottom picture there, those orange hoses are high dielectric strength hoses. So for applications where you want to, say, float your module